We're going to be doing a lot of calculating, a lot of problem solving, a lot of trying to explain what's going on. And so it's important that we know how to do that quickly, make approximations, and also when we get a result, check to make sure it seems like it could be correct. So the first topic I want to talk about here is dimensional analysis. And this is where we consider the units on the measurements or the variables in a problem. So we have a couple of rules with units in math. And this is similar to with variables, right? You can only add an x to another x and combine that to get 2x. If you want to do x plus y, you can only write that as x plus y, right? You can't combine them unless they're the same thing. Same thing with units. We can only add and subtract the same units. But just like in math, we can multiply an x and a y and combine them. We can also do the same with units. So if you have meters plus seconds, you can't do that. You can't add meters to seconds. But if you have meters times seconds, you can do that, and you can get complex units of meters seconds. So what does this mean for solving a problem? Well, at the end of the problem, make sure units make sense. For example, if I'm solving a problem and it asks me to find the distance between two houses, I do a bunch of work and I end up getting that the distance between the two houses is 5 seconds. That doesn't really make sense to have an answer of 5 seconds because usually when we measure distances, we're using meters or centimeters or kilometers or something like that. So what you should do when you're working on something is check at the end, are these the right kinds of units for the answer that I should be getting? If so, great, that means it's less likely you made an error. If it doesn't make sense, that means you probably did make an error somewhere. The next way that we can look at or check our answers is by looking at the order of magnitude and doing what we call Fermi calculations. So the order of magnitude, a quick math refresher, that's how many powers of 10 a number has. So we can use scientific notation to easily compare those numbers. So 1,000 is 10 to the third. And that's 10 times bigger than 10 squared, which is 100. So just kind of knowing powers of 10, that's a good way to think about answers, right? If we want to think about distances, 1 meter, that's, roughly the size of a person. 10 meters, that's roughly the size of a room, 10 times bigger. 100 meters, that's roughly the size of a building. 10 times bigger than that. 1,000 meters, that's roughly, the size of a couple city blocks. And so if you're doing a calculation and you're finding something that should be able to fit in a room, you're finding the size of a table, you would expect it to be, somewhere between 1 meter and 100 meters, somewhere in that ballpark, or between 1 meter and 10 meters. This is the idea here, is that we have a rough idea of about how big our answers should be. And these Fermi calculations are a way to estimate the order of magnitude for an answer. And so this is a calculation where you just ballpark the numbers. You're not caring about if it's completely accurate. You're just trying to get a feel for about how big should this number be. So I'll give you an example here. How many steps are there to the top of the IGA building? So I'm just going to run some numbers in my head. I know that we've got 6 floors. I also know that between each floor there's one of those landings, right? Because the stairs, you've got kind of this sort of situation going on. And so from the 4th floor to the 5th floor, there's kind of these 2 landings or these 2 sets of stairs. So I'm going to say there's 2 landings per floor. And then I'm just going to pick a number, right? The number of stairs for each of those landings, I'm going to say it's about 10. Is that accurate? I don't know, but I know it's close. I know it's more than 1. I know it's less than 20, so 10 seems like a pretty good number to pick. And so if we multiply all those together, 10 steps for every landing, 2 landings for every floor, 6 floors, we get about 120 steps. So I know that there's about 120 steps to top the IJ building. If you did this yourself and you got 150, or you got 100, or you got 90, we're all about the same. We're looking at, 100 in that ballpark. So if someone got 1,000 from some calculation, we'd know, okay, there's something wrong there because there's no way it should be that big. Or if someone got 10, we'd know there's something wrong here. There's no way it should be that small. So this is just a way to kind of get a rough idea of how big it should be. If someone got 200, then you might think maybe that's too big, but at least it's close, right? Because it's still the same magnitude. We're still looking at hundreds as opposed to tens or thousands. And that's the idea behind Fermi calculations. You're trying to get just a rough power of 10 magnitude. So if you look at your answer and it was way different from when you did the in detail calculations, to go back and double check.